So hopefully you've had a chance to read the materials so I don't have to do the whole sort of background. I'm going to do a kind of high level overview of the case that I asked you to read about for the pre-read. And maybe one thing you'll want to know, and as we go, I had a role in the resolution of this case or the dealing with it because it was taking place at the University of Minnesota where I used to be on the faculty before I came to Hopkins. So I have a firsthand back history and experience with this particular case. And everything I'm going to say to you is public. There's a lot of what seems very private information in both in the article I shared with you, but even more so, you're going to see pictures and hear information that isn't in that article, all of which has been made public by the family. So I'm not disclosing anything that would be a violation of their privacy or confidentiality. So let's get started. And I guess maybe say one more thing before I do that, which is, as you know, this is a two-part course. So today we'll talk about this sort of historical case, which took place in the late 1990s and into 2000, which you'll see on the final slide of the presentation today, has some resonance with the discussion that we'll have next week, which is about genome editing. So it's a little bit of a kind of historical trajectory here, which wouldn't have been maybe obvious from the way the description was written. So hang in there and hopefully that will become clear as we go. Last thing I'll say, it'll be hard to do because I can't see the chat function while I'm in presentation mode on my computer. And we'll leave, I promise we'll leave time for conversation and discussion. But as we go, if there's anything that is unclear or I have not described well or you have a burning question about, I'm totally fine talking as we go, but you'll have to somehow signal that you wanted to do that. So I don't know, Vicky, you can keep track of that or watch the hands raised, or people can just talk, and I'll stop and I'll happily manage it that way, and I'll keep track of time. So with that, let's move on here. So this is a story, as you know from the reading, which is a real case, and it's a case of what has now been termed savior siblings. So as it says here, it's creating a donor to help treat a child who has a particular form of leukemia called Fanconi anemia. And the way to do that is through a cellular therapy. And so the story is based on some sort of underlying facts. I'll do this really fast because you've read about it. So Fanconi anemia is a leukemia it's a genetic form of cancer. It's almost always inherited from your parents. It's a recessive genetic disease, which means that it sorts like this. For those of you who are in school and studying science, this will be very familiar to you, but for others, this may be sort of back from your high school and college biology. This is just Mendelian genetics. So when you have a recessive genetic disease and in this case, two heterozygous, so two carriers mate and have children, this is the way they would be predicted to assort. So the children that are born from two carriers sort this way. So a quarter, 1 out of 4, will have no gene. They won't get the bad gene from either parent. Half will be like the parents. They'll have one of the genes that would cause the disease and another that would not. But since it's recessive, they're not affected. They don't get disease. And then the problematic is the final 1 quarter who get the bad genes from both parents and therefore get the disease. And if you are in that unlucky 1 quarter, this is what happens. There's something termed dysmorphologies. It just means that there's certain problems in development such that parts of the body are not developed as they should be. So the children who are born with Fanconi anemia don't have thumbs, they have fused joints, and they have an incomplete gut, which can be, all of those things can be treated with surgery. There's surgical interventions, but the problem is they get leukemia, and depending on the particular mutation, and there's some variation in the gene, they get leukemia around the age of 6 or 7. Some can be a little sooner, some can be a little bit later. And to give you a little bit of a spoiler, it turns out that the Fanconi gene is a BRCA variant, which is a breast and ovarian cancer variant. And so it turns out that a carrier for FA is also a BRCA carrier. So mom in this case is a BRCA carrier who didn't know that until she had a child with this disease. So when a child is born and identified as having Fanconi anemia, they then begin to think about doing what used to be called a bone marrow transplant, now called a hematopoietic stem cell transplant, because the cells that make up the blood supply, that's hematopoietic, can come not only from the bone marrow, but also from umbilical cord blood. So when a baby is born, the cells in the umbilical cord blood include the cells that will become the bone marrow cells. And through physiology that we don't really understand, when a baby takes its first breath of air, the oxygen in that air tells the cells that had been in the circulating blood that would be hematopoietic stem cells to go to marrow. And the marrow is in your bones. The largest reservoir of that is in your pelvis and your hip bones. But when a baby is born, some of the cells that would go to bone get stuck in the umbilical cord. So umbilical cord blood can be collected and infused, as would a bone marrow transplant. For that to be effective, the donor of those cells has to be something called HLA match, as it says here on this slide. That's human lymphocyte antigen, and that's the immune compatibility between the donor and the recipient. The people who are the best donors from the purpose and perspective of HLA are your siblings, because that's the most genetically related person to you, not your parents, right? Not your grandparents, not your cousins, but your sibs. And so the first question is there a sibling in the family who can be tested for HLA compatibility with somebody who would need a transplant? If not, then one level removed would be other members of the genetic family. And then if nobody in that circle is available and compatible, then pools of adult donors are available through something called the National Marrow Donor Program. It's a great organization which matches willing stranger donors for people who don't have members of their family to be donors. And then lastly, there's an increasing collection of umbilical cord bloods when women deliver babies, and those bloods can be stored. They can be frozen and stored and then tested and matched for infusion in the way that I'm describing for this particular story. Okay, that was fast, but hopefully understandable. The second part of the story that I need to just share with you, the technical part, is represented by this photograph and this cartoon. So the photograph in the upper left is a human embryo that is being held in place by a pipette on the left. That sort of rust orange color is a pipette that's holding that human embryo in place. So there's obviously some high magnification going on. And then on the right is an even finer pipette that is being put up to a nick that was made in that developing embryo by a laser. So this is outside of a woman's body, an in vitro embryo. A few of you said something about IVF. So this is an IVF embryo outside the body just a few days after fertilization. And there's only 8 cells in the embryo at this stage. You can even see them and count. That's kind of in 3 dimensions. You can see there are 7 remaining. 1 has been aspirated out. So the pipette on the right has a cell in it. It's been sucked out of the hole there in the embryo. And this is known as pre-implantation genetic diagnosis. So a cell is effectively biopsied out of the developing embryo. So if you think about IVF, and the cartoon on the lower right there is meant to represent how IVF works. 1 egg, 1 sperm mixed together in a petri dish, or a sperm sometimes injected actually into the egg, creates a fertilized egg. That starts to divide, first into 2 cells, that's 1 division, a second division, 4 cells, a third division, 8. So this is a 3 divisions post-fertilization embryo with 8 cells. At this stage, all of the cells in that embryo are totipotent. They can become any of the cells in the developing embryo and eventual, hopefully, baby. And so taking 1 out turns out not to harm the developing embryo. Sometimes even 2 of the 8 are removed, leaving only 6. And the embryo just goes about its business, and the cells continue to divide and fill in what had been removed. Because they are totipotent at this stage. The cells that are removed have their DNA taken out, and by a technique called PCR, polymerase chain reaction, it's multiplied up, and the DNA can be tested. And so you can do genetic testing on the cells that are taken from that developing embryo, and then you know about the genetic makeup. of that embryo. So that's PGD, the D being diagnosis or testing of a pre-implantation. So before the embryo is put into a woman's body, that biopsy is done and the testing can take place. So PGD is an important technique for the story I'm going to tell you about a little girl with Fanconi anemia named Molly Nash. That's the story you read about. Molly Nash was born and with this disease. She came to the University of Minnesota, where I was on the faculty at the time, when she was about 6, because she was starting to develop the signs of leukemia. So her family knew that she had this disease when she was born because of the physical traits. I'll show you a picture in a minute. But they only came to Minnesota with her from where they lived in Denver, Colorado, because there was a physician still there who was one of the world experts in treating children with this disease. His name is John Wagner, if you're interested. Molly was the first child of the Nash parents, whose names are Jack and Lisa. They didn't know that they were both carriers for FA, but they turned out to be, and they were unlucky in that 1 out of 4 chance, right, happened with their first child. They wanted to have more kids, but they realized it's a pretty bad disease and they didn't want to have another. So one thought is, let's get pregnant again, have another baby, and then do prenatal testing. So amniocentesis or chorion villus sampling, and make a decision about whether to keep the pregnancy. And you want to also potentially have a baby that could be a donor, cord blood donor for Molly, who is 6. So realized she didn't have any sibs to be a bone marrow or cord blood donor. They then figured out PGD might be a way for them to be much more efficient at doing this, which they used, as you know from the story. So they had IVF in Denver, where they lived, and it turned out that nobody in Denver or anywhere else in the country would do PGD, not because they were worried about identifying which of the embryos that might be created by IVF in Denver were positive for Fanconi anemia, but because the parents, Jack and Lisa, had the idea, believe it or not, they thought of this themselves, that they could not only test for Fanconi negative embryos, but those that were negative for the disease that Molly had could then be tested for HLA compatibility with Molly. So they would choose only the embryos that were both negative for the disease, but also could end up being a good match for Molly to be a cord blood or bone marrow donor, right? So the second part is what gave people pause. And when we have the conversation, I want you to, tell me what you think about that second part. So the first part was something people had been doing with PGD for a while. That testing embryos for disease was something that had been done for, by that time, probably 15 years already for PGD. So add another 20 years to that now. So that was the challenge. And the only place that would do that second round of testing was in Chicago. And they literally flew a technician from Chicago to Denver, where the biopsy that I showed you in the previous slide was performed. And the 1 or 2 cells were then taken back to Chicago, where the testing was performed, and they would phone then back to Denver and say, okay, in this round of embryos, embryo number 3 is only one that's both FA negative and an HLA matched to Molly. They had to do that through 5 cycles of IVF, which is not there on the slide. So 5 cycles of IVF, not just 5 cycles, to achieve a pregnancy with a matched embryo. There were only 2 embryos that had both FA negative and HLA matched status to Molly out of 27 embryos that were made during those 5 cycles of IVF. If you're familiar with IVF, you can't do 5 cycles in quick succession. That happens over many months. Not pleasant for Mrs. Nash to go through. Lots of drugs involved. It's not a pleasant procedure to have eggs removed from your body after hyperstimulation of ovaries to make more eggs than otherwise would be the case. Anyway, it's not an easy thing to go through, and she had to do that 5 times to get to not 1 but 2 embryos. The first implantation was not successful. The second was. The embryo from that second of the 2 of 27 implantations resulted in a pregnancy, and a baby was born, as it says here, in August of 2000 in Denver, named Adam. He was named, I would ask you, if you were all sitting in front of me, why Adam was his name. He was named Adam for the reasons that you, I'm sure, have figured out from the story, because like in the story of Genesis in the Bible, Adam's rib was taken to create Eve. And so they thought very much that a piece of Adam would be taken to save his sister Molly's life. a little heavy, a lot of pressure on a newborn baby that you're named, you know, because you're going to save your sister's life, but that's what they did. And it turned out a prescient name for him. The cord blood was collected after he was born in Denver and flown to Minneapolis, the University of Minnesota, where the transplant was performed. And it sounds a little more complicated than it is. It's just hanging a bag of, in this case, cord blood, or it's the blood that has the stem cells in it from it's a transfusion, effectively, an infusion. So there's no invasive, pardon me, procedure for Molly, nor is there an invasive procedure for Adam to collect the cord blood. Remember, it's just the leftover blood from the umbilical cord after the baby is born. 100 days there is an important milestone because that's how long you wait for engraftment after the preparation of the recipient, which requires chemotherapy and radiation to eradicate all of the cancerous stem cells that are causing leukemia. So at 100 days, it was announced that the cells in Molly and Adam's bone marrow were the same. So it was a successful engraftment, and they returned to Denver, where they came from and still live, in January of the following year. So happily ever after, in a way. I'm going to talk about ethics momentarily here. So here's a photo. You can tell from my telling of the story who's who. That's Adam, obviously, on Molly's lap, and you can see in this photograph that Molly has a kind of misshapen wrist and she doesn't have any thumbs. That's one of the dysmorphologies that happens with kids who have Fanconi anemia. That's Lisa, obviously, and Jack, the parents. That picture was taken at the Mall of America, for any of you who are familiar with the Midwest. I don't think anybody mentioned that they were from this part of the country, but inside of Mall of America is an amusement park, which at that time was called Camp Snoopy. It's now, I think, been renamed SpongeBob SquarePants Park. But at the time it was Camp Snoopy, and this is right before Molly went into the hospital for the last round of chemotherapy and radiation, and they asked her what she wanted to do, and she said, I want to go to Camp Snoopy. That photo ran all over the world. Remember, this is pre 9/11. And so this kind of stuff got huge amounts of media attention. And as did they, as did the story, as did the University of Minnesota. And I got sucked into the sort of, what do we do about this part of it. Fast forward a little bit, that's a photograph from the Denver, Colorado Monthly called 5280, the Mile High City. You can see that Adam is there, 6 years old. Molly, that many years older. The Miracle of Molly was a successful, a kind of great story about happily ever after. Molly was cured. Adam, happily lives with the family, and off they go about their lives. This book you may have read or seen the movie based on it, was based on this story. So Jodi Picoult wrote this bestseller about the Nash story, although fictionalized, and it was two sisters rather than a sister and a brother. And it didn't go so well. If you've read the book, she actually called and met with the family and Dr. Wagner and myself, and we all thought she was going to book about the heroism of parents who were working and doing everything they could to save their daughter's life. And the story, of course, is a little more dark than that. I won't ruin it for you if you haven't read it. So, fictionalized version of a real story, a lot of drama around this, a lot of holding of breaths about whether this would work. It was the first time there ever had been a savior sibling attempted, and it happened to be successful, and it happened to be this particular case. So I'm going to pivot here and shift gears. I've been talking too long already, and talk about ethics for a few minutes before we break for our discussion. So again, if I were in the classroom with you, I would ask you this question and you would answer, but I'm going to do it for you. So what are the ethics features here? So what's at issue when we think about this particular case? And realize this was 1999, so it's a long time ago. Certainly in the pace of the emergence of biotechnology and how we use them, this was an early on, really interesting and controversial approach. So one of the issues that came up in the discussion and the way the media covered it was the parents were wrong. I mean, I'm putting words in the mouth here, but this is how it got portrayed, for choosing the trait of the child we call Adam. And you think, well, wait a second. In ethics and genetics, we've been talking about this for a long time, and we thought there's certainly a way to draw a line between what's acceptable and what's not from a perspective of using a technology like PGD to test embryos and decide which ones to implant and hopefully have a child. And so the way we would do that is to say it's fine to avoid disease, and PGD had been used for a long time already by the point of this, even by the point of this story happening, for things like cystic fibrosis, which is the most common inherited genetic disease. So it was used to help families decide whether or not they wanted to implant certain embryos when they knew that they were at risk of passing on a genetic disease. And so the distinction was between disease traits and non-disease traits, as it says here on the slide, with the idea being it's ethically acceptable to avoid or prevent harm in the future child. But the line is between that and non-disease traits. And the non-disease traits we worried about were things like physical or behavioral characteristics like you see here, with the idea being it's better for my child to have a trait that confers musical aptitude or athletic skill or maybe intelligence if we could figure that out. These things are not understood yet such that we could test for them, but we thought, well, the line between those two seems pretty clear. It's okay to avoid disease and prevent harm in the future child, but it isn't really a sufficient kind of provision of benefit to say, well, I want one with blue eyes, or that will be over 6 feet tall, or that will have certain, skills. And that's what we thought people might use it for. We didn't think that they would use it for HLA compatibility. So the weird thing about this case was they chose both to avoid disease, right? They didn't want the child we call Adam to have Fanconi anemia, but they at the same time wanted him to have a trait that would serve not his interests, but his sister's interests and their interests too as parents. So they chose a trait in their future child that would benefit Molly, which we didn't think was anything people would do. We weren't creative enough to imagine that. And so that's like a real puzzle. Like, where does that live in the, acceptable or not acceptable category? And so that's what we were confronted with as a matter of ethics. So here's one suggestion. We could say, parents should be permitted to do what's in the best interest of their child. But that seems a little bit too easy because Adam got brought into the world, and I haven't told you all the little details here, but among the things that are important is that Lisa Nash is a PICU nurse, a pediatric intensive care nurse, which is partly why she's so familiar with all these techniques. But more important for what I'm getting at is Jack Nash, the father, works in his family business, which is they own a chain of hotels in Colorado. And they were flying back and forth between Denver and Minneapolis in their private jet. And so I tell you that only because, from Adam's perspective, thank you very much for bringing me into the world, because if you hadn't chosen both to avoid Fanconi anemia and HLA compatibility, one of the other 25 embryos probably would have been implanted, and I would not have been brought into the world and get to live with a loving family in Denver, Colorado, and fly around on our private jet. So good for him. It's certainly in his best interest to have been brought into the world, right? Whether or not we think the choice of both disease avoidance and HLA compatibility with his sister are acceptable reasons. So that's probably too low a standard. So let me make it harder. One of the critiques of what the Nashes did, in addition to they chose, the traits in their future child, even though we said, well, that has happened for a long time. You don't like the particular traits they've chosen, but choosing traits is not something that is new. It's a technological innovation, but it's been around for a while. The second thing that the sort of critique centered around was this one. Why did the Nashes have Adam? They had a bad motivation for having this baby. They had him in order to save Molly. And so you sort of step back and say, wait a second, why does anybody have children? We want people to answer this, right? We want people to say, I want a child to be brought into the world to love and cherish, and the intrinsic value that children have, to treat them as an end in themselves. So that invokes the Kantian, the Immanuel Kant's imperative to treat individuals as ends in themselves and never as a mere means to the ends of another. Hang on to that, because that might matter for how we think about this case. And of course, we want people to say that's why they have children, but that's not the only reason they have children. They have children to carry on a legacy. That sometimes means a male in many cultures. It means having the last name. It means having somebody to bequeath whatever it is that you have to bequeath to the next generation. And in some cases, you start thinking about why people do that as being less like an end unto themselves and more like a mean to somebody else's ends. We also have more children because we don't think it's great to have only one. I make a joke about this when I tell this story, that my wife and I have 2 children. And part of that is because both of us come from families with 3, and no offense to the middle children, but neither of us are middle children. And the middle children in both of our families are ones we didn't think we wanted to recreate in our own family. So it meant either 2 or 4. 4 makes it really hard. You got to play zone defense instead of man to man, as they say. So let's stay with 2. And I'm being flip, of course, but people have all sorts of motivations for having children. By accident, you see how this goes. All right. So the point of this being, if we start asking this question, we have to ask really, are there any wrong reasons for having children? And do we really want to make judgments in ways that will affect what we allow people to do as a matter of policy? And if we were to say, even if the Nash parents were motivated to have the child we call Adam in order to save their sick daughter, is that a bad reason or a bad enough reason to do anything about it? You can tell by the way I'm saying it, I don't think it is. And I think we don't, for very good reason, query or examine or interrogate anybody's reasons for having children. We shouldn't do that. And if we aren't going to do that, why would we do it in this case? Okay, let me make it a little harder. So the Nashes did something that looks pretty laudable, right? They used PGD, had a baby, collected the cord blood, and saved their daughter, Molly. But they didn't have to do that. They could have done everything I said, but not given Adam a name, but called him baby boy Nash, put him up for adoption, collected the cord blood, saved Molly's life, and gone home without Adam. So one question is that cross a line in a way that we would say is a mere means use, like Immanuel Kant cautioned us against? Well, that has some kind of an odd ring to it, because we don't think children who are adopted are any less worthy or worthwhile or belong in the world than children who are not. So that doesn't really seem to make sense, even though that sort of makes us feel like, wow, that doesn't feel right from the perspective of what the Nashes were motivated by. But do we then say they shouldn't be able to do it? That doesn't feel right either. It's a challenge here, right? So the ethics start to feel not quite right, but doing anything about them also doesn't feel quite right. For some, making it even harder, for others maybe not, you don't have to actually wait for a baby to be born for the same cells to be collected. You can do PGD, implant an embryo, and then have an abortion probably earlier than this, actually. It says 14 weeks, it's probably even closer to 10, 11 weeks, and harvest the cells from the fetal tissue that would then be the same cells that would be in the cord blood or bone marrow for transplant. So that's not a baby, but that certainly feels like something not quite what we want people to do. So get pregnant with the intent to abort to collect the tissue feels like a problem, but hard to figure out what to do about it. So the question I sort of asked and answered already gets brought up again. Should we assess the motives of people to have children? We don't do that in our country. And it's unprecedented to do it in countries that we think of as liberal, small L democracies. And we shouldn't, right? We have been historically willing to decide who and shouldn't have children. That's a bad place to be, and we shouldn't go there. And so how should we think about restrictions on reproductive liberty? It's an important question that we have to resolve if we think either of these examples that I've been really quick to summarize, or others that you might think of, are so problematic that we don't think they should go forward. The problem is they run up against fundamental commitments in countries like ours to respect reproductive liberty. So if that's not going to work, what do we do? Well, one thing to do would be to say, okay, we can't prevent people from having children, and we shouldn't, but we can prevent people from doing risky things to their children. And so we can protect the baby we call Adam from being harmed. So let's see how that plays out. So if the stem cell transplant that I told you was successful in the Nash case hadn't been successful, what would the Nashes be faced with? And it turns out they were asked that. I was in the room when they were asked that. Well, when we go through this and the baby is born and we collect the cord blood, there's a chance that it won't work. The thing we would then need to do is decide whether to take the baby and put him or her, not knowing whether it was going to be a boy or a girl, under general anesthesia and do a bone marrow extraction. So a big needle into a really small baby, and do that under general anesthesia. Would you be willing to do that, knowing that there's some risk to your future child, but it will be something we have to know about, because if we need to do it, it will be kind of emergent. And the parents didn't miss a beat and said, of course we would do that, which is a little bit shocking too. So you're risking the health of your newborn to save the life of your other sick daughter. Terrible, it's kind of Sophie's choice problem, but that's one that would need to be dealt with. In addition, the bone marrow transplant requires lifelong immunosuppression for Molly, because she's gotten foreign stem cells into her body that need to be able to live there without being attacked by her immune system. Pardon me. Those drugs cause damage to parts of your body like your kidneys. And so at some point, she probably will need a kidney transplant. And who was a great kidney donor for her? Well, baby Adam, although now it's young man Adam, because realize he was born in 2000, end of 2000, and now we're in 2020. So he's pretty close to age of consent for himself. But that wasn't always true. So what would the parents decide if Molly needed a solid organ transplant? So what do you do about this? So the answer is this: we could have some kind of third-party review, a committee or something, that would have to make a judgment about when it was acceptable to expose the baby, we call Adam in this story, to risk for some kind of offsetting, probably not medical, there's no medical benefit to him, but some psychological benefit to him. So how do you justify what is effectively splitting apart the risk and the benefit? Risk to the baby for benefit to Molly and her parents. So in our country, we leave decisions about these kinds of things to parents. Other parts of the world, that's not true. European countries, they really would not permit the parents to make that decision themselves. We have a much more permissive way of approaching these issues in our country. And so it was fully the Nash parents' right to decide that, and their prerogative to decide that. They didn't need to, because the cord blood transplant worked, but it might not have. All right, let me try to wrap up quickly here so we have time for discussion. So all of this happening in a context of a policy environment that matters. And it turns out among the things that matters is this: there's been a embryo research ban in the United States since the Reagan administration, which means there's no federal research dollars to support research involving human embryos that either damages or destroys them, which pretty much means all human embryo research is not fundable by the federal government. As it says here, it's to prevent a dirty hands problem, so that members of our society, taxpayers who don't think it's acceptable to destroy or harm human embryos, don't have their resources invested in that. We can't sort of separate off, right? People who object having their money spent that way. And so we just have had a ban. There is no federal research on that particular area. As a function of that, there's no federal oversight. It's a kind of funky aspect of American civics that we tend to make policy for things that we pay for. If there is not public investment, then there tends not to be public rules, at least in biomedicine. So there's no federal law related to embryo research. There's just federal law that prohibits the funding of research involving human embryos. Important distinction. So that's one thing. That means there's no rules on something like this particular technology. The people who pay for IVF and other reproductive technologies tend to be the individuals themselves. There's not a lot of good insurance reimbursement. That changed a little bit with the Affordable Care Act. But when the point here is this is before the Affordable Care Act, and at the time, there was no insurer to say, we don't think this is a good thing for you to do. So there's sort of no third-party oversight because of a third-party payment. So there's no assessment of the appropriate use. The people who do this work in the professional setting, the reproductive technology folks tend to be very, very competitive. And since it's private pay, they tend to do things that people are willing to pay them to do, and they compete with each other for patients. So there's very little self-regulation, and they would say that themselves. I'm not disparaging them. It's an odd area of medicine. This turns out to be also a feature, these three things, a feature of the human embryonic stem cell research debate, which was raging somewhat after this story, but not a lot. Has since sort of died off because of technical advances, but it mattered for how our country dealt with that particular area of research as well. And then the last issue on policy is that this happened in 3 different places. The IVF took place in Denver, the PGD took place in Chicago, and the cord blood transplant and the subsequent treatment of Molly took place in Minneapolis. And so nobody was responsible for the whole thing. Everybody could point fingers at others and say, they decided that part, we didn't have anything to do with it, which meant sort of plausible deniability. So to finish off, there are a few things, and there are more than I have on this slide, but to sort of start the conversation. One thing is about equitable access to what was in their case a life-saving technology. It happened to work. Very expensive. At the time, it was $20,000 per cycle for the combination of IVF and PGD. And since it wasn't being reimbursed by third-party payers, remember they went through 5 cycles, that's $100,000 out of pocket cash money. That makes it very hard. They were people of significant means, and so they could afford it, but that's a real issue for others. And so how we think about, children who might need this kind of therapy and how to pay for it is important, and it's important in other ways today. It also made for the creation of many more embryos than would usually be the case in IVF. And in fact, remember, Mrs. Nash and Mr. Nash did not need IVF to have children. Molly was created the regular traditional way, and they only came to IVF because of their wanting to use PGD to create a stem cell donor. And so they had 25 leftover embryos, and someone has to decide what to do with those. This turned out to be a problem for all of IVF, an issue, I should say, for all of IVF. And there are literally millions of embryos that were not implanted that are frozen in freezers all over the world, and there are not clear rules or guidance about what to do with them, certainly not in our country. So to sort of wrap this up, the limitation of what could be done here is really only limited by what the technology permits. And so there were charges at the time, remember this was early 2000s, of designing babies, but that's not what was happening. We're going to talk about designing babies next week. It was really about selecting from a menu of the characteristics that could be understood at the time, and that list grows as we know more about genetics. And so there have been, for instance, this is pretty blunt, but PGD used for sex selection, which is not a waiting technology. We know how to tell X from Y chromosomes. And so people deciding which embryo to implant based on whether they want to have a boy or a girl baby. So sex selection by PGD, as well as selection of what some people consider genetic defects. That's why there are quotes here. Inherited deafness is the case in point. We can talk about that if you're interested. So people saying, I am deaf, my partner is deaf, we want to have a deaf child because that's the only way they can be full members of our non-hearing community. And so they choose to implant embryos that carry what some would consider the defect, the mutation for inherited deafness, which is interesting. And then maybe just to wrap it in a bow before I show my final slide, the challenge here is that we've got what look like pretty close to mere means uses, or the potential for mere means uses of the child being brought into the world, the baby we call Adam in this case, butting up against procreative liberty. So 2 really fundamental ethics commitments in conflict with each other. So the segue to next week is this. So hard to see, even for me sitting really close to the slide, but that says September 16, 2019. So that's, almost 20 years from when the Nash case took place. But this is a story about using CRISPR, so genome editing technology, to do exactly what I just mentioned, but rather than make a lot of embryos and choose, and hope that you've got the right combination, use genome editing, CRISPR and other technologies, to actually edit the embryo that you are creating so that it has those characteristics, both FA negative and HLA compatible with the child you're trying to save. So using this new technology to do the thing that the Nash family did through a totally different approach, over 20 years ago. All right, with that, I will stop. Thank you.